We are going to start chapter 2. So I'll share my screen. So as you can see, chapter 2 is on kinematics. So things are going to be moving in this discussion. And there'll be several videos. I think there are 3. So we'll start out talking about displacement. That's the change in position of an object. So the object starts in one location, ends up in another. That change in position is the displacement. So we would write this as delta x. So the little triangle is the lowercase Greek letter delta. And in physics, it means change in. And for us, change in will always be the final minus the initial. So we're measuring the distances that you've traveled as x, the displacement. X with a sub f, this f is a little bit below the line, stands for x final, so your final position. X with a sub 0 means your initial position. So again, the 0 and the f are subscripts. They go a little bit below the line. They should be about halfway below the line and smaller. Don't make them the same size. Delta x is equal to x final minus x initial. So displacement can be positive or negative. It depends on the location of your origin. In this first example from the book, if we start out measuring right here, this is our 0, and we move to the right, our final position is 3.5 meters. Our initial was 1.5. Subtract the 2 and we get 2 meters. And it's a positive number because the student moved to the right. If the student had moved to the left, it would have been negative. In this example with the airplane, we have the passenger starting out in the front seat, walking to the back of the plane. So 6 is where we started, 2 meters is where we ended up. 2 meters minus 6 meters gives us negative 4 meters. The minus sign, unlike money, tells us a direction. So we will always start our problems defining a positive direction and a negative direction. So displacement's got a direction, positive or negative, and this all depends on where did you choose to have your origin. Distance is just the magnitude of the displacement. And so our distance traveled is just our total length. I am really not going to beat this to death for you. We are always going to assume that we're dealing with directions in class. It's just in this first little introductory that they care about. Are we just looking at total distance traveled, or are we looking at displacement? So you just want to think about it as you answer the questions. So there's a real difference between displacement, distance, and distance traveled. And in the book, there's a way to just verify that you have an understanding of that. So you want to look at it. At the end of chapter 2, there are problems 1 and 3 you'll want to look at. We need to talk about vectors and scalars and coordinate systems. So vectors have both magnitude and direction. For example, if I'm traveling 40 miles per hour north, that's my velocity. How fast, excuse me, and in which direction. A scalar has only magnitude. So 40 miles an hour. If you look down at your speedometer in your car, it's a scalar measurement. It's only when it's coupled with which way are you pointing that we have a vector. So we will assign a direction to be positive or negative at the start of any problems that we work out that have vectors in them. And I will emphasize this over and over again. Normally we'll make up and to the right positive, but we don't have to. If everything's going down, I might make down the positive direction. So we move on to time, velocity, and speed. So time, I wish that they were consistent, but they are not. Sometimes in the book they'll use a delta t, sometimes they'll just use a t, and they might mean the same thing. Normally our starting time is going to be 0, in which case our ending time and our change in time are the same thing, just the total time. You'll get the hang of it depending on the equation and what we're dealing with. It really will begin to make some sense. So velocity, when we deal with velocity, time, by the way, is always lowercase t. Please don't make it capital. So velocity, we have initial velocity, final velocity, instantaneous velocity, and average velocity. Almost always, we're dealing with initial and final velocities. We use average velocity, but not really. I think you'll see why in a minute, and maybe when we do some examples. So average velocity is your change in position divided by your change in time. So average in physics is written as the letter of the alphabet with a bar over it. So V bar, again, this is a lowercase v, not a capital. V bar is delta x divided by delta t. Remember, delta is change in, so that would be x final minus x initial over t final minus t initial. So V bar is the average velocity. The delta means change in, and these F's and zeros are subscripts, so they're a little bit below the line. Now, when we deal with this, we almost never really need to write that V bar equals. We almost always just need this last part of it, that delta x over delta t is V final minus V zero. Oh, I'm sorry. Yes, I screwed up. Okay, maybe we do care about V bar. I'm getting ahead of myself mentally. I apologize. So average velocity is change in distance divided by change in time. We will move ahead. So if your average velocity is positive, you're moving in the positive direction. If it's negative, you're moving in the negative direction. I promise we'll keep up with our plus and minus signs. Here's where my brain was going before our notes. Our special case is when velocity changes uniformly with time. And this is actually the form of the equation we use a lot. It's that the average velocity is change in distance over change in time, which is V final plus V zero over 2. Remember up here, these were x's over t's. Here we've got x over t, but we've also got velocities. So average, if your grade were calculated by a midterm and a final, your average would be the midterm plus the final divided by 2. So our velocity, our average velocity, if it changes uniformly, we can look at the starting velocity and the ending velocity, add them together, divide that sum by 2, and come up with our average. And this part of the equation is the one we're going to actually use quite often. So delta x over delta t is V final plus V zero over 2. You don't really need to worry about the V bar part. It just comes about in how we define it. So speed is a scalar. Remember, we have scalars and vectors. Vectors have magnitude and direction. Scalars only have magnitude. So if you say you're going 40 miles an hour, that's your speed. It is not your velocity. So your speed, you can have positives and negatives, and we will deal with them all on an individual basis. We want to look at this diagram from the book. It has graphs showing us position, velocity, time, position, velocity, speed, all three versus time. Let's look at our graphic. So position versus time. Time, you'll notice, is on the horizontal axis. You will notice for our graphs, they all have a title at the top. When you do a graph for me, it will have a title at the top. Whatever's listed first goes on the vertical axis. Whatever's listed second goes on the horizontal axis. let's look at those two axes. So each axis will have a title, and in parentheses, you'll have the units it's measured in. So if time's on our horizontal axis, we are measuring it in hours. Position on the vertical axis, we are measuring it in kilometers. And you'll notice that 0 starts our graph, and we don't have any big breaks. So no starting at 0 and then jumping ahead. We want to be consistent. Another thing you'll notice that the two axes don't have the same kind of divisions. On the horizontal axis, I go 1/10, 2/10, 3/10, 4/10, and on the vertical it goes 1, 2, 3, 4. So you can have different scales on the axes, but we don't have broken scales. In physics, we almost always have time on the horizontal axis and distance or other things on the vertical. On this one, we travel in the positive direction, we stop, we turn around, we come back to our starting point. So if we look at velocity versus time, again, this one, we would end up with a positive velocity until we stopped. And then when we come back and go in the opposite direction, that's a negative velocity. So we'll have numbers in the positive velocity direction and in the negative, so above the horizontal and below the horizontal. So sometimes you need a graph that has both positive and negative in the vertical direction. Sometimes you just need positive. And then lastly, if we look at speed versus time, well, our speed didn't change. Apparently, we were going so many steps a minute or an hour, and we just kept right on. We just did an about face and continued on. And here's our about face corresponding with this switch from a positive to a negative velocity. So speeds, because they don't have a direction, we don't think of them as plus and minus. So we will stop with that.